Okay, so in the last video we looked at how to apply finite differences to various derivatives that might arise in our differential equations. And in chapters 8 to 9, then we're going to look at how we apply those to boundary value problems first in chapter 8, and then initial value problems in chapter 9. So in boundary value problems, the distinguishing feature is that we have a domain, say an x and y, x, y, and z, and on every boundary we have boundary conditions, so it makes it a BVP, a boundary value problem. We'll first look at ordinary boundary value problems, and then we'll look at partial differential equations that are boundary value problems. We'll develop the methods for ordinary BVPs, and then we'll extend them to partial differential equations. And here's we haven't had any Dilbert comics for a while, so there you go. Okay, we're going to look at a specific example. It's the extended fin problem, so heat conduction in an extended fin. This is something that might be used to cool electronic devices, such as a computer chip, for example. But the way we're going to use it is that we're going to use it to apply our general numerical solution procedure, which we discussed several videos ago. Remember, that was the three-step process, going from the real, actual physical problem to a numerical solution. So we'll walk through steps 1, 2, and 3 one by one for this particular problem. It's a very useful one. It ends up being one-dimensional, so it's relatively straightforward, but it's interesting because it is physical. So let's look at a situation where we have our fin, like so. Here's the base. So this could be, for example, the computer chip that's being cooled. The base of the fin will have a temperature TB, and then the x-axis is going to go along the length of the fin. X is equal to 0 is at the base, and x is equal to L is at the tip. So we're going to have air, or some fluid, that's passing over the fin, cooling it. So it's pulling air away from the base and then convecting it away into the air. It has a temperature T infinity and a convective heat transfer coefficient H. And then that's going to cause a convection heat transfer from the fin. Now the material of the fin itself has a property K, that's the thermal conductivity, which relates to how quickly the heat transfers into and out of that material. So that's the basic schematic there. And we're going to assume, you'll see this in the next slide, that this is a one-dimensional problem. It only depends on x. That's an okay assumption as long as this is a fairly long and narrow fin. And we'll walk through the other assumptions as well. Okay, so the governing equations, that's step 1 of the numerical solution procedure. So we start with the actual real problem, which we just sketched on the last slide. And then the first step is to apply conservation of mass, momentum, and energy as appropriate, any assumptions and models that make sense for this particular problem. And that will produce the governing equation from step 1 of the numerical solution procedure. So the governing principle is conservation of energy. So we'll apply that. We're going to assume that the heat transfer in the fin is only a function of x, so it's one-dimensional. Again, that's a good assumption for a long, thin fin, not necessarily for a short, stumpy one. And we're going to assume that the convective heat transfer coefficient H is a constant. This is sometimes okay. I mean, it's one of those assumptions. It's actually a terrible assumption in reality, but we'll apply it because it makes our problem quite a bit easier. When you do that, I won't go through the derivation itself, but when you do that, you end up with this equation. You'll find this in any undergraduate heat transfer book. This is the one that I used in Prepare and DeWitt many years ago, but when you take MMAE 323, if you do for your ME majors, you'll be able to find this equation in there. The capital T is the temperature. The A sub C is the cross-sectional area. You notice it will allow that to change with x along the length of the fin. A sub S is the cumulative surface areas from the base, so it starts at 0 at the base and it increases along the length of the fin. H and K again are the convective heat transfer coefficient and the thermal conductivity. And you see here T infinity, so you see all those parameters in here. So this is a second order linear. These coefficients here in parentheses they look complicated, but they're known. They're variable in general, but they are known. So this is a second order, that's a highest order derivative, linear ordinary differential equation that we need to solve. So that's our boundary value problem. That's essentially step one. Now we're going to simplify it a little bit. We're going to take T minus T infinity, just subtract off the ambient temperature just to make our lives a little bit easier, and we'll call that U. So U is going to be our dependent variable, and that is the temperature minus the constant ambient temperature T infinity. Again, it doesn't change the problem significantly, just makes things a little bit easier. So then here we have our second order ordinary differential equation. The F, G coefficients here and here are given. Those are the same as before. And then the H, I've included the H for generality, but here H is 0. When the right-hand side is 0, we say that the equation is homogeneous. It's just a fancy term for something being 0. Then the boundary conditions, U at the base, we'll call that U sub B, is TB minus T infinity. And then at the tip, U is U sub L, which is TL minus T infinity. I think I forgot to include TL on here. Yeah, so let's do that. So the temperature at the tip will be TL. So TB at the base and TL at the tip. Okay, so we have our boundary conditions. We call these Dirichlet boundary conditions because we're specifying the temperature at the base and at the tip at both boundaries of the domain. So this is step one. So that's going from the real problem, the actual real problem, getting the governing equations by applying any models and laws. So that's step one. Step two is the discretization. So step two takes the differential equation, and then we'll discretize the domain and the equation to get a system of algebraic equations, which we'll then solve in step three. So in step two, we're going to take the domain, the x domain, from 0 to L, and divide that into I, capital I, equals subintervals. So the length of those delta x will be L divided by I. So each little delta x, as you'll see here, is just the length divided by the number of intervals. So we go from the base at x equals 0 to the tip x equals L. And we're going to number these using the index I, starting with 1 at the base and going to capital I plus 1 at the tip. So if there are I intervals, there's capital I plus 1 points. Let me make a real I. There we go. So we go 1, 2, 3, 4, up to, then capital I will be the first one in from the right, and then capital I plus 1 is the boundary. A generic point I in the middle, we'll have a point to the right, I plus 1, I minus 1 to the left, and those are separated by delta x's, as you see there. So that's our discretized domain. So we've discretized the domain, and then we need to discretize the equation. The shorthand we're going to use is when I write f sub I, what we really mean is f sub x sub I. And same thing with g. G sub I is g sub x sub I, h sub I is h sub x sub I. So it's just a shorthand for f evaluated at x sub I. Same thing with u. So u sub I is really u sub x sub I. And so every point along our domain will have a value of f, value of g, value of h, of course all the h's are 0, and then a value of u, which is what we're solving for. So here's our finite equation, just like we had before. Here are the boundary conditions. U is ub, u is ul at the left and the right end respectively. We know the f and the g from before. So now we're ready to finite difference this thing using the finite differences that we derived in chapter 7. So here we go. So we have a first derivative and a second derivative. You see those here. First derivative and second derivative. So for the first derivative approximation, we'll use a second order accurate central difference, which you see here. It's the usual ui plus 1 minus ui minus 1 over 2 delta x. You can always think of this as rise over run. So 2 delta x is the distance between the 2 points, and we're taking the rise, the change in u over those 2 points, divided by the distance between them. And that is a second order accurate approximation. Then the second derivative, again, we use second order accurate central differences, so that's the ui plus 1 minus 2 ui plus ui minus 1 over delta x squared that we derived in chapter 7. And again, that is second order accurate as well. So we substitute those in. So here's the first derivative, here's the second derivative, and so we have the second derivative plus f times the first derivative plus g times u is equal to h. And that applies at every point x of I across the grid. So we collect all the terms together, so everything times ui minus 1, everything times ui, and everything times ui plus 1. And then anything that's known we throw on the right-hand side, that becomes part of our d. This should look familiar because we have three unknowns on the left, and we have our a, b, c, d coefficients. This is a tridiagonal problem, as you'll see, and that we'll see that in the next slide more explicitly, and that is solved using the Thomas algorithm. You notice I've also multiplied through by delta x squared. The reason for that is if you look back here, I have this delta x squared in the denominator. So if I multiply through by delta x squared, that eliminates that. That gives me a delta x times these other terms. And what that does is it makes the terms order 1. So you notice the a, b, c, d coefficients are all order 1. Well, d is not, but a, b, and c are. They're order 1 numbers rather than being really big or really small. Generally, we like to avoid that when we're using numerical methods. Now let's look at the boundaries. So remember our boundary conditions. U sub 1 is U sub b. U sub I plus 1 is U sub L. So those are the base temperature and the tip temperature. Now because we know those, when we apply our difference equation, 8.4, for I is equal to 2, so this is our difference equation for I is equal to 2, with A2 U1 plus B2 U2 plus C2 U3 is equal to D2. But we already know U1. U1 is the base temperature because when I is 2, I minus 1 is 1, U1 is the known temperature from the boundary condition UB. So because UB is known, this term is going to go on the right-hand side of that first difference equation. We're just looking at the first difference equation in our system of equations. So then the first one is B2 U2 plus C2 U3 is equal to D2 minus A2 UB. Then similarly at the other end, so at the tip, I is equal to capital I, we apply that to the difference equation. And so now we have I cap I U cap I minus 1 plus B cap I UI. But then the last term, which is CI times UI plus 1, the U cap I plus 1 is known from the boundary condition here. That is UL, that's the tip temperature. So once again, this term, the CI times UI plus 1 is known. That goes over to the right-hand side, CI UL, where again UL is the right tip temperature. So that is the last equation. So we've revised, updated the first equation and the last equation according to our Dirichlet boundary conditions. So that gives us then a system of equations for the interior points. So the interior points are when I is equal to 2 through capital I. So that does not include the left boundary, does not include the right boundary, because those values are known. Just the interior values 2, 3, 4 up to capital I. So when we write that out in matrix form, we get this big matrix problem. So here is that first equation that we just did. This is for I is equal to 2. The last one's for I is equal to capital I. And you'll notice I've highlighted in red the D's, the right-hand sides of the first and last equations that include the two boundary conditions at the tip and at the base. All the other ones in the middle from 3 through capital I minus 1, those are all just the general equations ABC, all the way through. So we've adjusted the right-hand sides to account for the known values in the boundary conditions. This is clearly tridiagonal. We have the B's down the main diagonal, C's down the upper, A's down the lower diagonal. So we can solve this using the Thomas algorithm, which we discussed back in, I believe it was section 3.3 3.2, I think, if I remember right. So we discussed how to solve these tridiagonal systems using the Thomas algorithm. So that is then step 3. So step 1, get the governing equation. Step 2, discretize the governing equation using finite differences. And then that results in a system of algebraic equations, which is what we have here. And then step 3 is to solve that system of equations to get the actual numerical solution. And in this case, we would do that using the Thomas algorithm. So you'll notice when we write these difference equations, so we have the differential equation, which has derivatives in it. Then we have the difference equation, which is after we apply the finite differences. The difference equation, by convention, is written with unknowns on the left and knowns on the right. So you'll notice anytime I looked at a term, I said, oh, well, I know everything, and we put it on the right-hand side. We've multiplied through, I said this before, we've multiplied through by the delta x squared so that all of our ABC coefficients are order 1. And that just makes them nice numerically, so we don't have to worry about numbers getting too big or too small when we do our numerical calculations. Now, if you remember way back when we discussed, I believe it was in chapter 2, I think it was 3.2.2, if I remember right, we talked about diagonal dominance and conditioning and the condition number and so forth. So remember we had that to be diagonally dominant meant that the main diagonal coefficient by magnitude was bigger than the sum of the magnitudes of the off diagonals. So for a tridiagonal system, that means that BI is big, at least as big as A magnitude plus C magnitude. And that would ensure that the system is well conditioned so we can get a numerical solution without any issues. Okay, so we'll discuss next time a more realistic boundary condition at the tip.